Hello and welcome to University of Michigan course EECS 367, Introduction to Autonomous Robotics, and Robotics 511, Robot Operating Systems. I am Professor Chad Jenkins, and now I'm going to give a lecture. This is my lecture on motion control and PID servoing. And so this course is this lecture is trying to help students along to do our second project to simulate and control a pendulum, a simple pendulum, and for some of the graduate students, a double pendulum. And so before I jump into that, I just wanted to reemphasize that I'm in my house again. We're still in quarantine. My kids are upstairs studying. They're in class right now. I'm down here taping, so if you hear any noise or anything like that, that's still us just being normal people living in our house. But I think this is a great opportunity to sort of put these lectures down and make them available. And I wish the best for all of the students right now. I know things are pretty intense, and I appreciate everybody's patience and all of the interactions that we're having on the discussion server. This is really about how we can help you guys be better roboticists as much as possible. And so I'm going to go through some of the slides that will help you finish the second project, and then from there we're gonna move on to forward kinematics after that. And so with that, I'm going to just jump back into my lecture here. A lot of what we do for motion control and PID and just your basic PID servo can help you control an inverted pendulum, such as a Segway here. I refer to this informally as my smooth criminal lecture. So this is inspired by when I see people on Segways. They remind me of Michael Jackson doing his dance routine. If you've never seen Michael Jackson do the dance routine for Smooth Criminal, you should watch it. It's a great video. I remember this from high school. I was in high school when this came out. I'll give you a sense of how old I am. But Michael Jackson's amazing, just an amazing performer. And if you don't know what that move is, where he leans over, that is called the anti-gravity lean. And so it really is sort of, when I first saw it, I was like, how do you do that? I will let you look up and see how he did it. It's actually pretty cool. But it's great seeing other people from around the world do the anti-gravity lean too. I can't get enough of watching people do this. These are amazing videos. I love this. I'm to some extent, I wish I had the ankle strength in order to do this. And so this is just really this is amazing. There's tons of videos like this. They're really great. And people are often thinking about how to get robots to do this too. So this is part of our imagination about how we can make robots do Michael Jackson type dances and things like that. And while this is sort of this has been sort of just sort of our imagination, sort of like our dreams of being able to have robots do these types of Michael Jackson style dances. This is increasingly becoming a reality. So for instance, we have bipedal locomotion systems. So this is the Cassie Blue robot from the Biped Robotics Lab here at Michigan, that's led by Professor Jesse Grizzle. And so you can see the Cassie Blue is walking over the wave field that we have, and so and in addition, they've had robots such as this be able to ride segways. So sort of like a biped on an inverted pendulum. It's getting very smooth criminal to me, and so I think I love I can't wait to see the types of anti-gravity leans that are going to come from these types of systems. But you should note that if you're going to do this type of control for a robotic system, that control must have to occur fast and often, right? Your update has to occur continuously and always has to be updated. Just imagine if you just yourself, stop paying attention for a second while you're walking, you could trip over yourself and all sorts of things. And so I just want to show a quick example of what happens if you try to do an anti-gravity lean and you just sort of let your control go. You don't update for a second or two. You could get something that looks like this. And so not the best anti-gravity lean. It just means to show that our control has to happen fast. And we should think of sort of control, the communication inside of the robot, in order to do this, sort of like the central nervous system of the robot. That central nervous system, it has to run, quickly and continuously, over and over, to make sure that we can perform in the world. And the same thing happens for robots. So if we take our robot, so we take a fetch robot here, and we look inside of it, we see like what the communication looks like. A lot of that is sort of, just like we have our brains, we have the computer that sits inside the robot. That brain basically controls everything, and so that really is the heart of making things happen. But similar to the way we have electrical communications in our body, we also have an Ethernet switch inside of our robot, and a main board that does a lot of the communication from the brain out to the joints, out to our actuators that are going to make things happen. Those actuators then have their own control systems that are allowing us to move, that produce the motion that we create. And usually for a robot, these loops have to run at about 1,000 times per second at minimum in order to produce the types of control behavior that's gonna allow our robot to function properly. And so this joint control happens really fast and very often. And when we're thinking about doing this, we should think about, well, what is actually doing this types of control for us? We can do this control in software. That means that we would have to have some sort of guarantee that the control is happening at a prescribed rate and is happening quickly. Usually we'd use something like a real-time operating system to do that. So or some sort of system that provided this. So there are frameworks out there, robotic frameworks such as Oracos that could do this. When I was coming up, we used VxWorks a lot. There are Linux has real time kernels that can do this as well. But a lot of times, what people do is instead of trying to do this in software, they'll actually do it in hardware. So if we drew a line here and we said, what's sort of the hardware software boundary that we'd see in our robot, the motor control, what sits inside the motor control boards that actually do the updating 1,000 times per second actually sit in hardware. So they're dedicated hardware that run these routines bare metal. And those motor control boards are responsible for doing this. So that sits in the hardware. And so what happens and this is just one particular configuration, is that when we're seeing these happens, that you have things at the application level that send actions that they want to execute to the controllers. And the controllers, what those controllers do is they generate set points, desired locations, desired states for each of the joints. And then those desired states are given to the motor control board, and that motor control board is essentially trying to update send motor commands that will allow the joints to achieve that desired set point state, given that it knows the proprioception from the robot. It knows the current state of every joint. And so this loop right here that the motor control board is doing is a lot of what we're trying to have our robot do for motion control. And so the motion control is really about at sort of a low level. How can we control every joint such that it achieves and maintains a desired state or set point through applying motor commands, given that we have the current perceived state, proprioceived state of the robot. And I should also mention that I made up this word, proprioceived. It doesn't actually exist in the dictionary, but it is sort of it's sort of an extension of proprioception. And the root of proprioception really comes from two words. It's sort of a blending of two words. Proprio, which means of one's own body, and then received, and received. And so you sort of bring those together. And so that's why I sort of make up proprioceived. Forgive me if I'm abusing the language. And so if we think about how this relates to our to the sort of robot operating system stack, it sort of fits in there. And so what we talked about last lecture was how we could do dynamical simulation. and simulate these types of robots. And now we're going to talk about on top of that how we can do feedback control. And so this is that. And so that is the feedback control part of of this task is what we're going to do in this lecture. Coming back to Project 2, what Project 2 really sort of brings these two ideas of dynamical simulation and feedback control together. And so if you remember from the past, what we did was we talked about how we could simulate a simple pendulum. We derived the equations of motion for it, as well as sort of highlighted what we could do for a double pendulum. We talked about a number of integrators, numerical integrators that could be used to simulate these equations of motion forward in time, so we could get a physical simulation of these systems, which could apply to many different types of robots. And so now we're going to take it and do what we call proportional integral derivative control for 1 degree of freedom robot. And we're going to put this all together at the end of this lecture. And so what can you do with the Pendularm, right? So why are we doing this project? It seems like this is a very simple thing. It's not really, it may not be, it's hard, sometimes it can be hard to see how this relates to the type of robots we'll be dealing with in the world. But just simple PID control from the pendulum can be applied to many different circumstances. And so I just wanted to give the PID control that we have that we're using for the pendulum could be used in many different circumstances. And so I just wanted to highlight one of those that was the sort of special to me, and that is this inverted pendulum. And so a couple of years ago, a student who was taking my class, I covered this lecture, and the student came up to me and said, so he started asking me all these questions about PID control and how we can do it and implement it. And I answered all the questions. I was sort of like, well, why are you interested? And he's like, well, I'm taking 473 and I want to do an inverted pendulum and like a differential drive inverted pendulum. And maybe I could use PID control for it. So I started going through how we could do that. And, I didn't think anything of it. I just said, all right, sure. You can, this is how you can do it. And the semester went on. And at the end of the semester, the student came up to me and said, and showed me this, this is just showing the system in action that he made for 473. And I was like, wow, that's cool. And it was amazing. Just from our high level discussion, he produced this system and like with any sort of student project for a semester, it was still a work in progress. But given that he built all of this and just got the PID control working, got something that was reasonably stable, I found thoroughly impressive, and I just liked it as something we can do using PID control. And so this is just very basic. I mean, this was rough, but it worked pretty well, and I'm sure he got even more refined by the time they finished that project. And so if you're a robotics graduate student and you're wondering why you're doing the balance bot in Robotics 550, I'm responsible for that to some extent. So I taught Robotics 550 in fall 2016. And Peter Gaskell and I, we went back and forth about things we could do where students could get more hands-on, more dynamic systems. And so using that inspiration, Peter really did a great job of putting the balance bot together. And at the time, you actually had to build your own balance bot, such as the one that Kevin French and his group did. But I think this is really just sort of like, it's a canonical sort of task in robotics, the inverted pendulum. And so I just really love that. And so this is just one example, but we use PID control in all over the place. And so just as one example, so if you're an undergraduate student, you're thinking about what you could take after 367. There's also 467, which is the robotics major design experience course. And so one thing that we had students love doing in this course is making robots that can draw. And so this is a robot arm, simple Dynamixel based robot arm that's drawing pictures. And so what happened, in order for this to work, at every joint in this robot arm, we have to run a servo, typically a PID control servo, that is going to allow the robot to move its configuration to desired poses, such as hitting a desired target location for the end effector or the tool, so that we can perform, so the robot can perform in a functional way. And so PID control is all over the place through all of these systems. And so before I jump off into talking about PID control, I just want to talk a little bit more about come back to some of the things about simulation, and how that could be used for how we think about our control systems. But let me start with something fun. And so I'm going to start with this just little demo right here that I found on the web. So what you're seeing in the browser right here is just a cloth simulation implemented in JavaScript and HTML5. And so what it's using, and so when I click on it, you can see that it'll do just a cloth simulation right here. I ripped it. I put a little too much force. Let me start over. Here we go. So I'm gonna try it again. So here's our cloth. I'm just trying to give it just a slight little pickup right here with my mouse, and then I'm gonna let it fall and pick this one up here, and then let it fall, and then I'm gonna be a bit rougher with it, and then just rip it all apart. And then and that's horrible and terrible, but then I can always reload and I get my cloth back. And so this is just really a fun demo right here that sort of shows what we could do with physical simulation. It's pretty cool. I love it, actually. I really can just watch this all day and play with this. It is really amazing. So what you were seeing with that was actually a Verlet simulated mass spring cloth. And so this is what you're doing in this case is you're representing this cloth as a network of point mass nodes. So you essentially have a collection of particles. Every element in the cloth here is a particle, and then you connect these particles together using high stiff springs. And so so these springs essentially keep these particles together such that they keep the structure of the cloth. And so if we wanted to make this on our own, we would just start with point mass particles. These point mass particles, we would, at every time step, we would apply gravity to them, and that would essentially make these particles fall down. But in addition, we would also, after we did that, we would apply the spring force constraints that would make sure that these particles kept a particular distance from each other and tried to remain there as well as possible. And so these are springs with high stiffness and the rest length. And the rest length is essentially how far away they should be along the cloth. Just noting that the force that's applied to, using the spring constraint, the force that's applied to one particle is the negative of the force that gets applied to the other particle. And so we can do this, and so I won't go through the details of this, but we can essentially enforce these spring constraints through an optimization that would relax these constraints. We just sort of do this over and over and over. And so this is how we can make sure that or at least to our best approximation, try to keep the particles in their right relative positioning. And so I just want to show that this isn't just a case of this works for one example. And so you could go to 3JS. So the same 3JS that we'll be using in this class for forward kinematics that actually is using to render the Pendularm. This is available on the web as well. And so this is our Verlet simulated cloth. You can turn the wind off. And so that takes some of the forces away because you can apply wind as another force. You can have a ball go through it, and you can see how the ball interacts with I need to turn the wind off. So you can just see how the ball interacts with the cloth and pushes it. And one thing I think is pretty cool is that you can toggle the pens, so you can actually take the pins off and just see it hanging this way. And then bring the pens back in different forms. Maybe we're going to have this one over here. Then we bring them all back. This suggests that we could also come back and revisit the pendulum that we covered last lecture. And in this pendulum, what we should note is we use what was called generalized coordinates. That means we were simulating the motion of the robot arm of the simple pendulum here, strictly with respect to its own degrees of freedom. So we were looking at the evolution of the state of theta over time, and we had our equations of motion essentially governed, said how these dynamics would evolve. But there's another approach to doing this as well, and that's where we could use maximal coordinates, um, where we simulate the location of individual bodies and then maintain their relationship through spring constraints or some other constraint. So in this case, we could consider what our pendulum is the bob of the pendulum is its own particle, and then we keep that particle attached to the axis, to the rotational axis, via a spring. And so this is something that we could try directly. And so I've implemented my own maximal coordinate pendulum arm. Let me go over to the browser and show you what that looks like. So this is my maximal pendulum arm. When I reload it, it's going to start up high, and then the pendulum's going to come and swing down. And like our pendulum in the past, it's gonna swing backwards and forwards, going through the zero location. But one thing that you should note that's different with our maximal pendulum arm is that it's losing energy. You can see that as I'm going through, at every swing, the swings get smaller and smaller and smaller. And that's partially, due to the fact that what's happening is that at every time step, I am the pendulum bob is moving down with respect to gravity, and then we're reinforcing the spring constraint with respect to the fixed point. And that means that we are not necessarily conserving energy. So we're not obeying essentially the law of conservation of energy or momentum or anything like that. It produces a result that looks good, but may not necessarily be physically accurate. And so it could be a good, but this is a lot less work to generate. To implement. And so this is just a sense of what a maximal pendulum arm could look like. So from this maximal pendulum arm, one question would be, or if you go back to the last lecture, what would a maximal double pendulum look like, and how much work would it take to implement one of those? And I would like to say that I can do even better than a maximal pendulum arm, double pendulum. What I can do is I'll actually make a 5-link pendulum arm, and that is something that's relatively easy to do. And so I'm just going to show you an example of my maximal 5-link pendulum arm. And so let me go over to my browser and I'll show that. In the case, this is my maximal 5-link pendulum arm. It's not swinging. If I wanted to swing, I could just let it do this. And so this is just the pendulum arm swinging. But I've actually actuated it. So there's actually a controller that works on it. So I've implemented both a PID controller that tries to make that is working to get the robot arm to go to a particular state. But I've also implemented what you'll see later. What we will do later on in this class is an inverse kinematics controller that's going to have the robot try to reach out and have its end effector touch this desired location right here, which is the blue dot with a 0 next to it. And so what we should note with this is that I can make a robot arm, even though this doesn't look nearly as aesthetically pleasing as the pendulum arm that I have in 3JS. This type of system can reach out to this is another valid way of simulating a robotic system, but it has certain advantages and disadvantages. I can add new links, new structures to this very easily because I have an engine that just takes these links and puts them together, and then all I'm doing is just adding constraints between them. And so you can see that it reached that goal and then is now finding then there's a new goal to hit. And so I can make this really fast. I can implement this really quickly. I just can't necessarily ensure that I'm going to obey many of the physical laws. Similar to that, I can do certain things with this that might be difficult in generalized coordinates. So if I click on a part of my robot, because it's just springs, I can stretch it out and move these in different ways. And so I can just move my robot arm and then let it go. And so you can see the springiness of it. I can also like with any other with my generalized arm, I can just turn off the servos and then bring them back up. but I can also just let it just let's just stop enforcing sprint constraints, and then I don't have then I don't have any then my robot just sort of dissolves, right? Um, and so this is something that we can do. Also, I would just say if I went back to my single pendulum and I reloaded it, what you can, and just to see this a little bit more clearly, is that if I turn off the spring constraint, my particle just sort of goes away, and I can bring it back and let it swing again. But I can also, but taking the spring constraint away just sort of disintegrates my robot. And so so maximal coordinates is really what you'll notice that a lot of our simulators may use maximal coordinates and then enforce constraints, but that may not be, as you can't necessarily treat that as physically realistic. So given that we have maximal coordinates and it's easier to make simulations in maximal coordinates, why should we use generalized coordinates? And this is even more so than just having high fidelity, more faithful physical simulation. Generalized coordinates also has a particular meaning for us in robotics that's important. And so when we think about those generalized coordinates, if we come back to our pendulum, you should note that when we're looking at our motor torques and how they're applied and the evolution and related to our system, that in our case, motor force is expressed with respect to these degrees of freedom. They're expressed with respect. They are a much better match to how our controls are actually going to be applied to the robot. And so these motor forces are really important. If you look at some of the simulations in maximal coordinates, you'll note that they have motor structures that they put on top that give you to simulate what the motors would look like. But it's a patch that they have to do because on the maximal coordinate system, a maximal coordinate simulation, because they just don't have because that's something that because they're not it's not as seamless of a match as generalized coordinates. And so when we're thinking about how our motor forces are expressed, we should assume that in our pendulum, we have a 1 degree freedom motor at the pendulum axis. And that what we want to do in terms of maintaining control is we want to have that pendulum that we want to have our pendulum arm, our robot arm, maintain a desired set point angle. And the motor's job in this case is to apply forces so that represent motor commands that will get us to this desired angle and maintain that angle. And so this comes back to to what we think of as a servo. The servo has motors in it. These are our actuators, but it also has proprioception, which is our optical encoder, and then we have a controller, which is an H bridge, and that H bridge regulates the current that goes to the actuator that expresses our motor commands. And so we should look inside of this servo to get a sense of how these components fit together. So if we were able to look inside of this servo, what we would see is that we have a control signal. And that control signal will send what's called pulse width modulation, that signal to an H-bridge controller. The H-bridge controller would then be responsible for taking that current, for taking that control signal and then sending current to the motor that would then actually produce the desired motor motion about our degree of freedom axis. And so we can take each one of these sort of individually. And so when we think about pulse width modulation, this PWM signal, it has a periodic duty cycle. So there's a period of time that the signal will be active, and then during that period, you'll have a high voltage whenever for the amount of time that the motor should be on, and the amount of time that the percentage of time at which the signal is high essentially is proportional to the speed of the motor. And so if you have your signal high for 50% of the duty cycle, then you will have then your motor will run at a particular speed. If it runs at 20%, then your motor will run at a slower speed. If you have it on at 100%, it's trying to run at full capacity. Although I wouldn't recommend that. Um, and so this pulse width modulation signal is then sent to in different way. That pulse width modulation is sent to four different switches on the H bridge. And so the H bridge has these four switches that are either on or off based off of the duty cycle that's sent to it. So we have those four signals that go in, and that goes into to switches for A, B, C, and D that you that are pictured right here. And then depending on which combinations of those switches are given to be on from the control signal, that depends on the behavior that the motor will actually produce. So for instance, if we turn on switches A and D, that will produce a forward spin of the motor. And conversely, if we have switches B and C on, that will make the motor spin backwards. As we go on, if none of the switches are on, then essentially we have an open circuit, which means we have no current and no torque. If we turn on C and D, or we turn on A and B, we'll have a negative torque, which will produce a braking motion for the motor. Something that we have to be very concerned about is that if we turn on A and C together, or B and D in isolation, that will not be good. That will be very bad. That will cause a meltdown of our hardware due to a short circuit. So you don't want that. And usually the H bridge will not let you do this. And so once we have that, so the job of the servo controller is to produce this control signal that will be sent to the H bridge and produce the motor control. And so we have to. So that servo control is oftentimes it needs to know the current state of the system. And usually what it uses is an encoder to send that joint state back to the controller. So the servo controller will take in a desired angle. The proprioception right here, the motor encoder will give back what the current state is, and the servo controller's job is to try to get those two things to align as best as possible by sending that control signal. We should note, and I won't cover this very much, but I won't cover it at all. This is the extent that I'm gonna cover it. We can use a number of different things to do proprioception. One common choice is the quadrature encoder. And that quadrature encoder essentially has an encoded disk, and then based off of sensing and that disk essentially usually goes from light to dark, or from occluded to non-occluded in the case of the light sensor that's shown here. And that'll essentially let you count up the number of transitions that you have from going from a light state to a dark, sensing a light state and a dark state. And that creates these transitions that we see in the signal. And that quadrature encoder essentially can count up the number of times you've transitioned, and they tells you how much you've spun. In this case, we're showing a quadrature encoder. I'll let you think about why we use a quadrature encoder. And so given that the servo controller's job is to take in proprioception and a desired state and produce motor commands to achieve that desired state, how do we actually implement the servo controller? And so let's go back to our pendulum and to get a sense of this. And so what our control scheme will look like on the whole is that we'll have some controller that will output a command U. We're going to call that U, and that goes into the plant, the dynamics of our system, and then produces a next state for a system, a resulting state from that action. And when we look at this and sort of that what these dynamics are called, or what the system is called, is sometimes also referred to as a plant. That represents the system dynamics as a function, so our function F here. And so we should note that our motor commands are used and that function encapsulates our equations of motion, and the motor command is the U inside of that equation of motion. So that U will relate to tau in the equation of motion that we had for the pendulum from last lecture. And so that's our plant. The servo controller is then given that system, given that plant, the servo controller's job is to take in the current state and the desired state, and then output an appropriate control commands based off of what is called a control policy. So the pi here is what's called a control policy. Whenever you see that as a function, that's usually what that represents. And we have two different types of control policies that we could think about. One is your open loop controller, where you have a controller that has a desired behavior and then produces control commands that are sent to the robot without any feedback back to the system. So it's just running open loop without response. And so there are cases where open loop makes a lot of sense. What we're going to talk about more in this class is closed loop control. That's what you'll implement, and that's where the state that results from the robot actually comes back to the controller, and the controller has to respond to this as well. And so this closed loop control it has many advantages to it, but oftentimes requires a little bit more, is a bit more involved. So let's start off with open loop control and say when should I use open loop versus a closed loop controller. And so let's start with some examples. So let's consider, you have examples such as like a robot in a factory, as we have up in the corner, or various types of toys or animatronics that you might see at an amusement park. Your Roomba that's cleaning on the floor, is that something that uses open loop control? Or maybe some of the control systems that that might be used in your everyday life, such as the thermostat that you use in your house, or the thermostat's used by your refrigerator. Should we use open loop control for that? Or let's say a lot of your commercial aircraft these days, when you take a commercial flight, a lot of that is done using control systems. So which ones of these should be open loop or closed loop? I'm gonna let you think about that for a second while I go get a little bit of coffee. All right. So let's take one example. Furby. That is not annoying at all. But Furby is one example of a pretty interesting open loop control system. I have to stop that. So one open loop system that we have with Furby is that it's interesting that one thing that you can do if you want to make things interesting things that behave, but also do it at low cost, because you don't want to pay a lot of money for a Furby. At least I don't. But what you can do is open loop control can be something that's implemented relatively inexpensively by putting all the behaviors for a control system on a single cylinder. So in this case, everything. So this is almost like a tape, like it's reading off of a tape, and so you can encode all the behaviors for this that you just play open loop onto this cylinder, which does very basic playback. And you can do this really cheaply in that, and then whenever you want to call up a particular behavior, you just move the playhead of the tape to a particular location on the cell, and then you just play it. And and this produces interesting behavior that is very compelling. It just goes to show that design sometimes is more important than sophisticated controls or sophisticated mechanisms. And this is pretty engaging because they've sold a lot of these. Similarly, you could have the animatronics that you have in an amusement park. This is for instance, this is a pneumatically driven character that's used at Disney. And so so if you're gonna create an amusement, a feature that has all of these different robots doing things, and you got to make a lot of them. And these robots aren't necessarily going to interact with anything. They're just going to, sort of do the same motions over and over and over again. You got to make a lot of them. Why bother doing closed loop control? Because you want prescribed choreography. That's more important. So open loop control makes a lot of sense, especially if you're going to do this at scale. And so there are reasons why you want to use open loop control, but for a lot of things that we want to do in this class, feedback control is a necessary. We need to close the loop for our systems because they need to respond to a dynamic world or just be able to respond to its own proprioception quickly. There are different types of feedback control, so you can have just sort of like you can create an arbitrary nonlinear control policy that that does something that you think is right, and so you can write the rules of your control policy if you want to. Another way to think about it is to have what's called negative feedback control, where you actually are phrasing some form of error. There's an error that's being expressed between the desired and your current state, and based off of that error, that's what's going to be used to express the control command back to the robot. And so one form of negative feedback control is PID control, and that is what we're going to focus on in this case. And so really, it's about minimization of error. That is how we're thinking about control in this case. And then there's also negative feedback control with the feed-forward controller. So the feed-forward controller may want to do something to adjust the system for things that you might expect. So if you know that you have to compensate against gravity, then you might use the feed-forward controller. If you need to, if you know that there's some sort of anticipation you want to do, you don't want to just react to error to the error that's happening, but you want to anticipate. That feed-forward controller can add compensation into the system to provide action, to provide motor commands towards that action that can be summed into the motor control. So let's go and focus on PID control. And what PID control is called proportional integral derivative control. And all of these are, and what this is really thinking about error, the error between our desired and current state, and then looking at them from different perspectives, where we are going to provide feedback correction based off of the current error, the past error, and the predicted future error. And the way we're thinking about this is it's sort of, and this PID controller will behave like a mask spring and damper system. And so let's cover that in more detail. But so when we're just noting for this case that when I for the pendulum that our state X is going to be the theta of the pendulum in this case for just the control part. And we're going to express our error signal as the difference between the desired state and the current state. And it's important that you subtract the current from the desired. Given that we have this error function, we can express the control signal in the form that we have at the bottom, and that means that we're expressing the current, past, and future as sum responses to each of those as a sum, a weighted sum. And so instead of trying to go through that equation, let's try to look at it from a more intuitive perspective. And I would say that let's consider how PID behaves with respect to the state over time. And so if we looked at time on our horizontal axis, and we start off with time at 0, and then on our vertical axis, we have the state of our system. Our desired state XD, let's make an assumption in this case that it stays constant. And so we'll have a constant desired state that is our set point XD. If we look at the evolution, and we want to just sort of look at this all the way up to the current time, all the way to the current time t. We're looking at this at this. We'll start off with our initial state x0, which does not have to be 0 itself, but I've just conveniently put it there. And this is going to evolve over time and bring us up to our current state xt. With respect to that current state xt, and this is just showing the evolution of what our controller might behave like over time. That current state xt, if we look at our spring term, if we look at our proportional term, what this is essentially an error, a spring error. We're considering sort of a spring that connects our current state to our desired set point state. And the proportional term represents this error as a displacement of the current state towards the desired state. And so you can almost consider a spring that's sort of bringing them together. And we weight that by some spring stiffness, as we'll talk about more. Our integral term is the response to errors that have occurred in the past. And what this integral term will do is it's going to continue to add force into the system until our error, and that's going to drive our error to zero. And we should note that what this integral term is doing is continually adding up the sums of past errors, and we're accumulating that. And once the error gets to zero, then we have no new error the integral term will add no new control force when it hits zero. Although we have to be worried that if it starts to add up, it'll actually lead to divergence from the set point instead of convergence. And so, thinking about how to minimize that sort of divergence or combat that divergence, we have the derivative term, which is really looking at the rate of change of the error. And so, in the rate of change, that rate of change of error is really to release energy from the system. So if I took like my past error and my current error, when I subtract them away, what you're really saying is my current error is trying to drive me to the set point, that term, but my past error is always going to oppose that motion. And by opposing that motion, its job is to release energy from our system and combat divergence from stability and the set point. If we looked at this with respect to a plot, so whenever somebody talks about PID convergence, you'll always see plots that look like this, where we have our desired set point, and then you'll see the evolution of the state over time. You can note that if we have really good behavior, so I may need to pop up in this case. So if we have really good behavior, what you'll see is that our system will come up, overshoot the set point a little bit, and then slowly come back to the set point and be able to provide this nice convergence back to the set point. If our system can be over stiff or be too or over stiff or just maybe too over controlled, we'll get a behavior that looks something like this, where we'll have vast oscillate. We'll overshoot by a lot, and we'll have lots of oscillations before we can get to the actual set point, and it'll take longer for us to converge. But more importantly, if your robot is doing this, you should note that your robot is like moving all over the place, and I don't want to be standing next to any robots that are doing that. So please don't do that. Conversely, your robot might be very stable but underpowered, and so it's just going to take a long time. It's going to start here, and then just take a long time to get to the it's going to take a long time to get to the actual set point, and do you really want to wait around that long for this to happen? And so there's some trade-offs here, and so that you have to think about when you're implementing your PID controller. So when we look at PID control, we can take a look at it as a spring and damper model that has a physical description. It has an analogy to physical models from physics that we can look at. So when we do this, we can isolate our P controller, the proportional term, and just think about that as a mass and spring model in and of itself. And this is really when you're looking at PID, the proportional term is Hooke's law, effectively. And so if you don't know who Hooke is, Hooke was a famous physicist, a part of the Royal Society, and was really a leader at the time. Unfortunately, in science, I'd like to think that we are a pure meritocracy, and we value ideas. Unfortunately, a lot of times science is a battlefield of ideas, and that in order for my idea to be right, your idea has to be wrong, and vice versa. And I think, unfortunate for Hooke, he got into it with Isaac Newton, who both was younger and able to change history after Hooke's departure from the field. And they were just not. It just was not a good dynamic, even though lots of great knowledge came from that. And so, this is just a reminder that we should be good. In addition to being good scientists and good engineers, we should be good citizens as well. There is karma in our field. But coming back to Hooke's law, what Hooke's law represents in terms of how we think about in terms of PID control is that the force that we're going to apply, the control force that's going to be output, is going to be proportional to our displacement from rest, or really displacement between the displacement as an expression of error multiplied by some spring stiffness, and that spring stiffness is something we're going to have to determine, and so that really is going to be the impact of the that really is its contribution to the control force that of the servo. We should note that Hooke's law itself, even though we have this linear relation, negative kx, that really is an approximation to how the spring behaves most of the time inside of most of the spring. And so we have this nice linear behavior for most of the time when the spring is compressed or elongated. But when you start to get to the extremes, then it goes very nonlinear. So we should note that Hooke's law is an approximation of the actual force relation. And so if we just look at the effects of the proportional term, that we can see that depending on what you choose for your gain, you choose as the stiffness, it can have a big impact on the behavior. So if I'm over stiff, then my system may oscillate a lot about the set point. And if I'm under stiff, it just may take a long time. And that we're always trying to tune it towards reasonable behavior. And so I have an example. Let me show you my Pendularm in action. So I'm trying to achieve negative 1.26, which is just over to the left side here. My overstiff controller is continually trying to do this, but it's oscillating. It's going back and forth about this vertical, and so it's really just sort of adding more and more stiffness, and we're creating these big oscillations that will never really be able to hit the desired, which is just if I can show you, the desired location is just right here. Wrong way. Just right here. We want to be at this desired angle, and we're just continually oscillating about it because our system is over stiff. I want to provide another example of something that is under stiff. So similar, we're trying to make the same get to the same location of negative 1.26 radians. And our understiff system just never really, it never really has enough power to get up there. You can see that it's going to try to get closer and closer and closer. So in this case, it will do it, but it's going to take a long time. And I don't have time in lecture to show this, but if you're understiff, we just don't have, we don't. This is just too slow, and so we can't wait for this to happen. And I'll just reload that one more time so you can see just the understiff system just can't get there. So it's going from swinging to just sort of sitting there and being very slow. So moving on back to our PID controller, let's also now think about not just the proportional term, because that alone is going to be very difficult in order for us to get the high desired behavior we want. Let's also think about, let's say we have an overstiff system, we could get that to potentially potentially produce stable behavior that leads us towards the set point. But we're going to have to release some energy out of that overstiff system, and that's where our damper comes in. And so the purpose of the damper, like a shock absorber, is to release energy from the system. And we can consider that is the purpose of our derivative term. And so if we assume that that we have a constant set point, we can note that our velocity in this case can just be considered the derivative of the state instead of the derivative of the error. And so if we have our spring and damper system like this, we can get different types of effects onto the system. So if we assume our proportional term is fixed, if we change our damping, that will essentially produce different types of profiles as we're trying to hit the set point. So in the green in this case, which my finger is trying to track, produces pretty nice behavior where we just overshoot and then we come back and we gracefully head back into the set point. If we're over damped, we have more damping. we can get a similar curve, but it's just going to take longer to hit there. And so you should note that there's a big difference between when our better damp system hits the set point and when our less better damp system hits the set point. If we have a less damp system, we're not removing energy as much. We can overshoot and then start to have oscillations again. So we overshoot in one direction and then overshoot again, and eventually we'll get back to the set point, but it just may take some time. And so that's not. So we'd like to have a system that provides better damping than that. And so we want to tune in that direction. And so I can show you. So here's an example of something that of a pendulum that I tuned with respect to both its proportional and derivative terms. All right, so let me reload this. And so in this case, I have the system here. I'll let this pendulum swing, and then after the pendulum swings, I'm going to start the servo, and the servo gets to where the desired location should be. It actually gets there pretty quickly, pretty reasonably. But one thing that you'll note is that we don't quite actually get there. And so even though it seems like I've produced stable behavior, what you'll note is that, and so I'm going to just use my cursor to show this time, is that my actual desired state is negative 1.26 radians, right? But where my servo controller has actually hit has been negative 1.23. And so what that is considered to be steady state error. So the pull of gravity onto the pendulum bob, along with the control force, it's reached equilibrium, but it's reached equilibrium short of where it should be. And so no new control force is going to be added by my P and D terms. And so I'm really just sort of stuck here. So in order to counteract the effects of steady state error, that is specifically why we include the integral term, the I term. And so the steady state error really occurs from equilibrium before reaching the desired state. And there are many different reasons why it could happen: external force, weak loader, low proportional gain, etc. And so the integral term is really there to counteract that steady state error and drive it to zero, even when this occurs. Our integral term, if we just looked at the integral term itself, we see similar sorts of profiles in this case, and so we can get behavior that is acceptable, that produces this nice slight overshoot and then convergence to the desired. And we should note that our integral term adds up quickly, and so if we tune it the wrong way, we can get big oscillations and very poor stability. And we could also just not use as much integral term, but that will lead to something that is stable but slow, but responds slowly. And so here's my example of a not awesomely tuned PID controller. So here's my controller. You can see what's happening right here. So I'm going to use my cursor to show this. Is that that this is the desired state is still 1.26, and our current state, even though it's in sort of steady state error, it's actually able to overcome this. And so once I have that, I'm going to let it swing for a little bit, and then I'm going to bring it back. And so you note that my system's case overshoots and then comes back down to the actual right amount. And so probably what's happening in this case is my proportional term, my integral term might be a bit too high. But I'm able to hit the desired target in reasonable time. Definitely not great time. And so I've seen much better examples of this. My other reference code has better examples. And so, but once I've converged, I can then change the desired set point to be whatever I would like for it to be. And that is how I produce the motor control for my system and move it to any desired state that I would like. And so that's my control of this robot arm. So one thing that should be clear after going through all of these terms is that implementing a PID controller, the PID algorithm, will not necessarily produce a good controller. The gains that you choose for each of these controllers, for the stiffness, the damping, and the integral compensation, really produce the behavior of the system more than anything else. And the gain tuning is, I'd like to say, is a science, but is really more of an art. Because we should note that what's happening through these gains is a number of things. It is doing an implicit unit conversion from angle displacements, from essentially radians into Newton meters. I think I'm gonna try to recall that off the top of my head, but into essentially a force. You're going from displacement to force, and so there's a unit conversion that's happening there. But also, encoded in this is also the dynamics of our system, right? We have this PID controller knows nothing about what's going on in the actual dynamics of the system. But yet it's able to produce this control by minimizing error. And so implicit, sort of implicitly, is these gains are defining what is actually going on in the dynamics of your system. There's a bunch of rules, or not rules, but guidelines for how you can for what each gain will do and how it'll affect the system. And so I just stole this from Wikipedia as one possibility. There's also more structured approaches to doing gain tuning, like Ziegler-Nichols, and so you can explore that on your own. But I can say that my approach to gain tuning goes something like this. This is sort of the artisanship of creating gains, is that I start all of my gains at 0. And then what I do is I increase my spring gain continuously from 0 until my system roughly meets the desired state. And that means that my P gain will most assuredly be overshooting and oscillating about the desired state. And so it might be wobbling back and forth over it. And then once I do that, then I'm going to start increasing my damping to remove energy from the system, and get this controller that approximately works from the proportional gain into something that will be stable, or something that is stable. And so producing that stable motion now means the thing that I need to counteract is steady state error. So once I have that, then I can start to slowly increase the integral gain until my system consistently reaches a desired location. And I try that for many different set points, and refine the gain to improve that performance. And so that really is what I do over and over and over again. And I try to get this to work. Everybody asks, how fast should their controller work? It depends, but if it's really working well, I've seen students be able to, they get convergence within a second, right? And sometimes even less than that. And so if your system, because we can apply as much motor force as we want in simulation, and so this is something that can be done. So if we put all of these ideas together into the Pendularm project, what we're doing is taking what we had from the last lecture about dynamical simulation, using the integrators that we have. So these here, and integrating over the equations of motion for the simple pendulum, and so that will produce something that looks like this, where we take our equation of motion and we encode it into the pendulum dynamics that are integrated forward to take our current state xt and as the position and velocity of the pendulum angle, and use that to produce the next state some delta time and forward. So that really was covered last lecture. And now then once you have that implemented, you'll on top of that use a feedback controller, and that feedback controller will then compute the error. So given a desired pendulum state, it will compute the error, take that error, then compute through your PID controller to produce a control, pendulum.control, will then be used within your equation of motion to generate the acceleration that you integrate forward to produce the next state. And this will run continuously over and over and over again. One thing that you should note, because we're doing this, because our gains are implicitly tied to a particular system, that if you change your system, that means you will almost assuredly need to change your gains. That system is defined by the mass of the pendulum bob, the length of the pendulum rod, the time step that you use. So that time step will change the behavior of the system, and so all of those are really important. I'm just going to show maybe a quick few examples of that. And so in this case, my pendulum bob is just I just made my pendulum bob really big, and so if I reload it, this is what my PID controller produces. What you'll note is my desired again is negative 1.26, and we're trying to reach that. You can see that it gets really close, 1.25. I didn't really have to change the gains here, but I get much different behavior in this because now these gains are still trying to have to overcome that much more energy. Also, one thing that I did here is I turned off the eye controller, the eye term whenever it hits the desired state, so you can just see the effect of steady state error. So it's climbing up, it gets to 1.26. And then once it gets close enough to 1.26, we turn it off, and then it comes back up. And so we'll I'll let that converge, and so you can see it one more time. Right. So similarly, we can make our pendulum bob smaller. And so I just turned this on. I started it, and our gains are just way too high for this smaller pendulum bob and pendulum length, and it just blows up, because we're just putting way too much energy into the system. This doesn't have to work for just the Pendularm. It could work for many other different types of systems as well. One thing that you'll see commonly in the controls literature is the cart pole balancer. And so I'm just sort of flashing the equations of motion for this. But our cart pole looks something like this. And so you can control the position of the cart. And then there's then it's attached to then there's a pole that's attached that can rotate, but you can't control that the rotational angle of the rod, only the positioning of the cart. And so what you're trying to do is keep the rod upright while and just through the positioning of the cart. And so this is just showing some examples of being able to do this. And so this is what you can have with a good control strategy. Additionally, you should be able to keep the pole balanced while changing the positioning of the cart, and so being able to move it to different locations while still keeping the pole upright. And even if the system goes out of stability, you should still be able to recover. And so this is just a really cool sort of video that shows this. We started with the inverted pendulum, and so the inverted pendulum I think is a good thing to look at, and really just your basic PID control works. And so to me, if I see something that's happening in Lego, right, that's happening with the Mindstorm kits, right, I oftentimes think that's PID that's working in order to make that happen. And so this is just showing an inverted pendulum that I believe is using PID control in order to produce this driving capability. And so that's what your segue is looking like. One thing that I should note before we leave this topic is that we've been treating dynamics in this case only as particles. But we should note that robot links are actual rigid bodies. And so now we're going to try to start to expand out into thinking about robots with geometry, robots that take up space and are not just point masses. So if we look at what we've been thinking about our pendulum as a particle, it assumes that our mass is a single point and only the position of a single particle is considered. But when we start to look at pendulum as a rigid body, we should note that each link is going to have a center of mass, and then mass is going to be distributed about that center of mass. And then we have to account for not just the position of this body and its center of mass, but also the orientation of the body and the coordinate frame that it exists on. And I took this from the SD-FAST. The SD-FAST tutorial. SD-FAST is the physics package that I started with when I entered into robotics, and so it's the original. It always has I feel like we're really just covering what you need to know to understand what's going on in that manual in this course. But I always recommend going back and reading that manual. I think it's really actually interesting. Get some real good insights. But when we start to think about rigid bodies, then we have to go more. Then we have to have something more than just Newton's equation, which really talks about the force, the translational force that's acting on the body. We also have to complement that with Euler's equation, which also talks about the angular. Also talks about the dynamics with respect to orientation in terms of the angular velocity omega and acceleration omega dot. And so mass in this case has an analogy of inertia with respect to our center of mass right here. And so this leads us to Newton-Euler equations of motion. If I take those equations of motion, I can express them in matrix form, and that gives us the expression right here. And so so the linear algebra refresher will be the next slides that are posted on the website. And this is expressing it with respect to one body. This is only for a single link, and this is respect to the body center of mass. But we could also express it with respect to any arbitrary coordinate frame, and this is just an expression that I stole from Wikipedia that says that. And even if you've taken linear algebra, you may not know what this operator means. That is a skew symmetric matrix, and so and skew symmetric matrices are very good for taking cross products, and so that's why we have that there. We should note that joints between these rigid bodies are now, so this is just a pictorial view of what joints look like between the rigid bodies. And so you have the center of mass, and then of the inboard and outboard body. And then for a hinge joint, for instance, you can have rotation about the axis of that cylinder. And so we have to consider the distribution of mass and inertia about this system. But what it also leads to is a more general notion of the equations of motion. And so when we think about the dynamics of these rigid body systems, it leads to a much more fuller expression that requires us to think about this in terms of where our variables now become vectors. And our configuration of our robot is now expanded to consider a number of degrees of freedom. So we consider the configuration of our robot to be expressed as Q, which is comprised of the configuration of all our degrees of freedom, Q1, Q2, all the way through Qn. And if we have a joint that is revolute, that is rotational, we express Qi as theta. Typically, we just denote as theta. And if it's prismatic, which means that it translates, then that's represented as d. Given that we can form a vector Q of this, so this is represented as set, but we'll think of it as a vector. Then our equations of motion roughly take on these terms, and that we'll take on these terms, and that we have a vector of all motor forces. So this is the motor forces applied to every degree of freedom as an n-dimensional vector. Force times mass times acceleration now becomes an inertia matrix M, which is, and that inertia matrix depends on is a function that depends on the current state of the robot. And so that inertia matrix represents times the acceleration of our degrees of freedom, Q double dot. That represents mass times acceleration. Similarly, we also moving on with our other terms, we also have to consider gravitational forces, frictional forces that may occur when we're in contact with objects, as well as centripetal forces and Coriolis forces. I would say just be careful with centripetal force. There's a lot of examples in the world where you should note that centripetal force can be a lot. Your tilt-a-whirl, your roller coasters, centripetal force is nothing to be messed with. And also there's the effect of the manipulator payload. So you can think of as you reach out to grab something. So I'm going to reach out, grab my coffee. So as I have my coffee, right, as I'm holding it, that affects some, that's the effect of having this object, holding on to it, and what that and I can translate this. I can transform the effects of trying to hold on to this payload to any of the bodies in my system using the Jacobian, which we're going to talk about later with respect to inverse kinematics. And so there's a number of approaches to devising equations of motion. In using for these cases. So you can take your Lagrangian that we covered in the last lecture and try to expand it out to think about how you can represent dynamics with respect to this formulation. But there's also other approaches. And so the one that usually comes up as sort of and is in the Spong book is the Newton-Euler recursion. And so it turns out that the Newton-Euler recursion is equivalent to the Lagrangian formulation, but it's a very different approach. Instead of being energy based, it's basically on knowing that you have balanced forces at your joints. And so whenever you have whatever force is acting on an outboard body, that there's an equivalent and opposite force that's acting on the inboard body. And so what we can do is develop a recursive algorithm that would go through our kinematic hierarchy and update each of our link based off of this notion of balanced forces. And so when we think about this recursion, this is just a quick review from the Spong book. Is that we'll start with our base link, and so when we start from our base link, we'll then compute the angular velocity that we have for link 1, and so we have that information already available to us. Then from that, we'll compute the angular acceleration that goes from link I to link I minus 1. We'll compute the acceleration at the end of the link, and then move that acceleration to the center of mass. And so that will provide our accelerations that we will propagate forward throughout the kinematic chain. And so we'll perform these steps over and over and over from the base link all the way till we get to the end effector. And then once we get to the end effector, we're going to come back and then we're going to update forces. And so we're going to start from our end effector link. We're going to compute the force exerted by link I minus 1 on link I. From the outboard joint to the inboard joint, or outboard link to the inboard link, and then we're going to compute the torque that's exerted, and that torque will then be the force. Those forces will recurse from the end effector link all the way back to the base, and that will give us that will update the forces that are being applied, and so or that are occurring in the system. And so this recursion allows us to do this simulation of rigid body systems. It's on my list to try to include this in this class, but we're already packed, and I worry that I need a pretty big refactoring of my code in order to do this. And so, but I would love if somebody in the class did that. You will note that there's an advanced extension for doing this without the big refactor of the code. So just a final note about how this fits to actual controls. So I'm giving, I'm not really a controls researcher. I'm not an expert in controls, but there are people that study this in much more depth. PID usually gets, is good enough for most of what we want to do, but there are more formal ways of looking at controls that can lead to more elegant and stable solutions with that can provide more that you can understand a lot more than just sort of like these gains sort of work. So we can think of PID for our pendulum as a linear system. So this is just this is stolen. This is stolen from when I took robotics as a graduate student, you'll notice a lot of the slides from that course sort of show up in these slides as well, such as this one. And so this is a vector matrix form of how we could think about PID as a linear system. But what it leads up to is a general form where you can say that the next state x dot of your system is equal to the current state times dynamics matrix A plus your controls U times controls matrix B. And so this leads to a more linearized state of linearized expressions of the control of the plant in the control problem. One thing that you should note that with our PID that we don't consider system dynamics as before. But you can account for those dynamics in the control problem. And so if we think of this model that we usually have for the planet is usually called a forward model. And so that is taking you forward in time. That's taking your state and your controls and telling you what your velocity or next state would be. We could also, assuming that the model is invertible, you could have an inverse model that said, well, our controls should really just, what we should do is take in a desired and know what our plan is doing. And maybe if we had an expression for this forward model, we could invert it in some form, and then our controls should naturally just drop out of the formulation. And so that's, so you could do some sort of inverse dynamics approach. I'm just sketching this out really briefly. Another approach is to think about optimal control. So the same way that our path planner searched over waypoints in order to get from a desired location from a current location to a desired location, you can do the same thing that includes a model of the dynamics explicitly. So if we have a cost function and we have a model of the dynamics, we can just explicitly search over possibilities instead of just sort of saying I have an epsilon hop from one location to another. That be the actual dynamics of your system. And so optimal control gives us an expression for doing this. And there's many different types of optimal control. At Michigan, I hear a lot about model predictive control, and in other spaces you'll hear about linear quadratic regulators, control systems. Those are viable approaches to think about search control as a search problem. And so we're going to move on. We're going to now jump into forward kinematics and thinking about how we can model our robot and draw it out in space and understand what the space takes up. In order to do this, you're going to have to need a little bit of refresher on linear algebra. And so I'll put slides up for doing that. But our next topic that we're going to get to is going to be robot kinematics. And so I just want to thank you again. So I'm gonna take my glasses off. I just want to thank you again for going through this lecture with me. Happy to answer any questions that people have. I think this is really just a start into, if you want to do controls, it's really a start into how you can think about it, and gives us enough to get the basics down, so you can get your robot systems working. And so I'm looking forward to what we do next. Thank you.